Hi everyone, my name is Yair, and today I'm going to present QuickShell. Sharing is caring about an RCE attack chain on QuickShare. So, this is me. I'm the security research team lead at SafeBreach. I have more than 7 years of experience in security research, including research on Linux embedded and Android environments. And for the last 4 years in SafeBreach, I've been mainly focusing on Windows vulnerability research and third-party apps that run it. This is Shmuel Cohen. He is a primary contributor to this research, same as I, so credit goes to Shmuel as well. Now let's see what we're going to talk about today. We're going to start with the reason for why we chose QuickShare as a target for this research. We'll then get a quick overview about the protocol that it uses, move on to see how we managed to fuzz it, and then see the research approach shift that we took towards logical manual search of vulnerabilities and the vulnerability discovery that came out of both approaches. Then we'll see a very unconventional and creative assembly of a remote code execution chain that we managed to achieve out of these vulnerabilities. And finally, we'll summarize with takeaways and the GitHub repository. So, for those of you who are not familiar with QuickShare, QuickShare is Google's nearby file transfer solution for Android, same as Apple's AirDrop. Now, the reasons for why we chose QuickShare as the target are a few. First of all, Google has recently announced a Windows version of QuickShare, allowing to share files between Windows computers and Android devices. And at CES 2024, Google announced that they're working with leading PC manufacturers like LG to expand QuickShare as a pre-installed app for Windows, making it a much more attractive target. In addition, QuickShare uses a variety of communication technologies, and as far as we knew, this was Google's first time implementing such communication technologies and using such APIs on Windows, so we assumed that there will be more room for mistakes. Furthermore, the only past research that we could find was from 2019, and it was done only on Nearby Connections API, since QuickShare didn't even exist back then, but only the API that it uses. It was done only on Android, and no CVEs were issued. Another interesting fact is that most of the application's code can be found in open source repositories, not all of it, but some of it at least. So concluding all of these facts together led us to evaluate QuickShare as a valuable and hopefully likely to be breached target. Our main goal was to achieve the first ever remote code execution on QuickShare. So to do that, we needed to start investigating the protocol, understand how it works. So the first thing we did was to find the basic two functions that allow to send and receive packets in QuickShare. These two functions, the read and write functions, as part of the class-based endpoint channel. Then deeper inside the read function, we were able to understand that received bytes are parsed into an offline frame object. Now, the offline frame object is a Protobuf object, and this is its definition. But don't be alarmed by the name offline frame too much, as this is just the base type for most packets that QuickShare uses. So from now on, I'll mainly refer to offline frame as just packets. Now at this point, our first tool for this research was born. It was called QuickSniff. Basically, the first version was implemented using WinDBG and PyKD. Then we improved it to be a DLL. And basically what it does is just that it hooks the read and write functions, then it parses the received and sent bytes into offline frame objects, and then it textually prints them. This allowed us to much better understand the protocol in its textual form and see really what happens during a file transfer session. And this is why I'm now able to provide you with a quick overview of the protocol that QuickShare uses. So, first of all, QuickShare is implemented upon an API that is called Nearby Connections API. This API allows Android apps to exchange data nearby regardless of network connectivity. QuickShare just implements its own implementation over that API. Now, a few interesting facts about Nearby Connections API is that it's based on Protobuf. For encryption, it uses the Google UKey2 library. In order to distinguish between different apps that use the Nearby Connections API, each app provides a service ID, and the API can be used in multiple connection strategies, including peer-to-peer, a star, and a cluster. Now, we will mainly discuss the peer-to-peer strategy since this is the one that QuickShare uses. And now let's see how a basic file transfer session looks like in QuickShare. So, the first packets sent by an initiator of a file transfer session are a connection request followed by a UKey2 client init packet that initiates the encryption handshake. Then it is responded by the server with a UKey2 server init packet, and finally again responded by the initiator with a UKey2 client finish packet, finishing the encryption handshake successfully, exchanging encryption keys, and from now on this makes sure that all packets from now on, all subsequent packets will be encrypted. After keys have been exchanged, both sides send a connection response packet indicating that they would like to accept the connection, and at this moment both devices are considered connected to each other. This is where the proprietary implementation of each app that uses Nearby Connections API begins. Now, when I'm saying proprietary implementation, I'm talking about a set of packet types that each app that uses this API can use. So far, we saw the connection request and connection response packets. From now on, we'll focus mainly on payload transfer and bandwidth upgrade negotiations, since they are the ones that QuickShare mainly use. So, let's see how QuickShare uses them. And as a reminder, this is where we stopped, just where the devices are connected and the proprietary communication begins. After that, both devices send a payload transfer packet. Deeper inside the payload transfer packet, we were able to see that the payload that it transfers is really another Protobuf structure, really another Protobuf packet called paired key encryption. So both sides send this paired key encryption packet, and then in the same form, both sides send a paired key result packet. At first, we were not able to understand the meaning of these packets, but with a few experiments, we managed to understand that the purpose of them is to enforce the device visibility modes. So basically, QuickShare offers device visibility modes that can define who is allowed to send files to the current device. Visibility modes can be, the visibility mode can be set to everyone, only contacts, or only devices that are linked to the same Google account. Now, all modes except your devices require physical acceptance of the receiver with the file introduction dialog. So after visibility modes have been enforced, the initiator sends a file introduction packet showing some data about the file that it would like to send. Then the responder is prompted with a file introduction dialog, hopefully presses accept, which triggers an accept packet back to the initiator, and only then the initiator sends the file itself over a payload transfer packet. So now we understand the basic flow of QuickShare's protocol from a network perspective. Let's take a quick look at how this looks like from a user's perspective. So we have a Windows computer that would like to send a file to Shmuel's phone, and the file is named malicious.txt. So we choose Shmuel's phone, then we get the file introduction dialog, press accept, and the file is now located in the downloads folder. So now that we understand that basic flow of the protocol, we can move on to fuzz it. We chose to fuzz the Windows application, so for that we use the most straightforward infrastructure for fuzzing in Windows, which is WinAFL, and for instrumentation we used DynamoRio. Then since we wanted to mutate only the values of the protobuf fields and not the whole protobuf structure itself and ruin its validity, we used lib protobuf mutator that is meant just for that. Then, with a few obstacles that we managed to solve on the way, we managed to get the fuzzer up and running. Then it was indeed pretty slow. We tried to optimize it in multiple ways, though it caused some race conditions and false positive crashes. So we stayed with this speed, but over time, the fuzzer did provide some crashes. So overall, it resulted 4 crashes, 4 reproducible crashes that we were able to reproduce each time. However, unfortunately, they were not exploitable. Another interesting finding by the fuzzer was a reproducible timeout. Basically, this reproducible timeout enabled us to bring QuickShare into a state where it continuously opens a file that we choose from the victim's downloads folder, where QuickShare's files are saved. So at this time, we decided to sum up our fuzzing adventures. We did get a fuzzer up and running, but it was pretty slow. It did get us some results, some crashes, but they were unexploitable. So instead of perfecting the fuzzer, we decided that we'll move on to manual logical vulnerability search, and then we just said, boy oh boy, we wished we had done it sooner. So the first vulnerability that we'll be talking about is the file acceptance bypass. So if you remember, in order to, not in order, but before the initiator sends a payload transfer packet with the file itself, then it first sends a file introduction dialog and waits for an accept packet to be sent. Only then it sends the actual file. However, when we thought about the fact that QuickShare's code is so generic and complex with multiple threads and async methods, then we just asked, what if we just send the payload transfer packet immediately without doing the whole dance of the file introduction packet and waiting for accept? Then this just resulted a complete bypass of the need for acceptance by the responder. We could just place a file in a victim's downloads folder without any need for the victim to accept, and this even bypassed all device visibility mode. Even if the victim device was set to receive files only from devices that are linked to the same Google account, then we could still just immediately place a file in its downloads folder. So without further ado, let's watch our first demo, which demonstrates this exact vulnerability. So here we have Shmuel's phone, and this will be our victim. So we see that this phone is set and configured to receive files only from devices linked to the same Google account. And we see that the downloads folder is empty. Now we'll move on to run our exploit from the computer. We're running it, and let's take a look at the downloads folder again. The file is now there. Great. So the second vulnerability we'll see is how we managed to force a victim device to connect to a rogue Wi-Fi access point that we decide on. Throughout QuickShare's code, there's a term called bandwidth upgrade negotiation. This term refers to the fact that when a file transfer session is running, then QuickShare tries to understand whether there is a better communication technology that it can use in order to improve the transmission speed. So QuickShare can upgrade the bandwidth to be Wi-Fi, Bluetooth, Wi-Fi Direct, WebRTC, or even open a Wi-Fi hotspot on one end of the devices and then provide the other device with an SSID and password to connect to that access point. Researchers have already shown in the past that this can be used for a man-in-the-middle attack, sniffing all internet traffic of the victim for about 30 seconds. Now, this was shown on Android, and since then, this was already mitigated by Google, and Android devices today, when they are connected to the Wi-Fi hotspot as part of a bandwidth upgrade negotiation. They're not going to the internet. They're not doing internet connection through that hotspot. However, checking this exact attack on Windows, we saw that the Windows device does use the internet through this Wi-Fi hotspot, so we can sniff internet traffic of a victim for about 30 seconds now. Okay, so at this point, we had 8 vulnerabilities at our disposal. The most critical vulnerability was probably the one allowing us to place file on a victim device, but this was not the remote code execution that we were looking for. So with the sentence that we invented, we thought that just like turning standard stones into deadly drones, which sounds pretty much impossible, we're going to turn these vulnerabilities into remote code execution. The abilities we had so far are to create files in the downloads folder without the approval of the victim. Then we could also sniff its internet traffic for about 30 seconds. We could also crash QuickShare in multiple ways, and we could also force QuickShare into a loop where it continuously opens a file that we choose from the victim's folder. Enumerating these abilities, we had a crucial insight. We understood that the downloads folder to which we can write files is the same folder where browsers save the files that they downloaded. And this led us to an idea. What if we could overwrite an executable that was downloaded to the downloads folder before it runs? If being a man in the middle can somehow help us know which executable files are downloaded by the browser to the downloads folder, and if we can somehow override them using our abilities, then this would lead to a remote code execution. That is because we'll be able to replace the executable with our malicious one, and then the user will run our executable. Okay, so the simplest example would be a victim that downloads the VS Code installer. We then override it with one of our vulnerabilities, and then the user will run our executable instead. And for that, we'll have to know the name of the executable that was downloaded. So we still didn't have all of these abilities, but since we assumed that the man-in-the-middle attack will somehow help us identify names of downloaded executable, we started with trying to make the Wi-Fi connection last longer. And then a very simple solution for that came up. Just crash QuickShare right after it connected to our Wi-Fi access point. Since QuickShare returns to its original Wi-Fi network only when the file transfer session is over, then if we crash it right after it connected to our Wi-Fi access point, then we get a forever lasting Wi-Fi connection. As regards to the crash itself preventing us from further exploiting QuickShare towards the RCE, this was not really a trouble because once QuickShare is installed, it creates a scheduled task that runs every 15 minutes and makes sure that QuickShare is running. If it's not running, then it runs it. So we can continue to exploit it. And so we have our first 2 links in our remote code execution chain, and we expect these 2 links to come in handy for identifying downloaded executable names. Now, let's see exactly how this helped us. This is how. Metadata matters. Basically, looking at this image, we thought that it explains exactly how we leveraged the Wi-Fi connection for identifying names of downloaded executable. It was indeed true that HTTPS, which is the protocol that files are downloaded over, is encrypted, though it still had 2 important elements in its metadata. And the first one is the server name indication extension. So basically, the HTTPS protocol is encrypted using the TLS protocol. Now, TLS starts with a client hello message by the client that includes the server name indication extension, indicating the domain that the client communicates with. Meaning that if we're exposed to victims' HTTPS traffic, Even though it's encrypted, we can still determine the domains that the client communicates with. The second element present as part of the metadata is the approximate size of the data that is being transferred from the server to the client, the approximate size of the download. Even though encryption might add some random padding, then the approximate size of the download stays relatively the same, and also an executable file is very likely to be much bigger than any other resource on the website, any other page on a website. So the conclusion is that if we know the domain that the client communicated with, and we know that the large file was downloaded from there, and we know the approximate size of that download, so we can probably also very accurately guess the name of the file that was downloaded from there. So for instance, if we know that 95 megabytes were downloaded from code.visualstudio.com, then we know that the latest VS Code installer was probably downloaded. And so we framed and defined our new man-in-the-middle technique more specifically. In order to be as precise as possible, we understood that we need to define what we called domain paths. A domain path is a sequence of domains to which we expect the victim to access until the download starts. So if we'll take a look at this example with Notepad++, then clicking on the download button on the Notepad++ website does not download the executable immediately, but instead it redirects us to github.com, which then redirects us to objects.githubusercontent.com. And if we'll just look at the last domain from which the executable was downloaded, we won't be able to determine that it's Notepad++. So we need to follow all the domains. So to conclude, this is how we defined the new man-in-the-middle technique. We start by creating a mapping between domain paths to executable that match these domain paths and their sizes, the sizes of the executables. Then we wait until the victim hits a certain domain path in a limited time frame, and we start counting the downloaded data. Finally, based on the downloaded size, we deduct the name of the executable or the installer that was downloaded. And so we chained another link to our RCE chain. Now we can also detect the names of executables that are downloaded by a victim. But with that being said, we still did not have the ability to overwrite files, but just to create them. But we didn't have to have this ability generically. We just needed to have it for our specific scenario when files are being downloaded. So what we tried to do was to overwrite a download while it's still ongoing, a download that is happening by the Chrome browser. But first, let's understand the basic download flow in Chrome. So when Chrome starts to download the file, it first checks whether it exists in a downloads folder. Then, if it exists, it decides that the file name will be added with a suffix with an index number surrounded by a parenthesis, and if not, it decides that the final name will be the same. Then it starts downloading the file, but into a temporary file with the CR download extension, and then when the download is done, it renames the CR download file to the final name that has been decided on at the beginning of that process. Now, because the decision for the final name is made on the beginning of the download process, we thought that there is a good chance to create confusion if we send a file with the same name right in the middle of this process. This will maybe fail Chrome in overriding the CR download temporary file to the file name, leaving our file in place. But as you remember probably, in order to accurately guess the name of the file that is being downloaded, we need to know its approximate size. And to do that, we need to wait for the download to be finished. So what we're doing is that we're waiting for the last TCP packet to arrive from the server, and then we hold it since we're the man in the middle. At this point, we know that the download has been finished and we know the approximate size, but the client does not. So what we try to do is right at this point, send a file, an executable file with the same name to the victim's downloads folder, hoping that Chrome will fail to overwrite it. But this did not succeed. The result was that Chrome just successfully ended the download and overwrote our file. But this was not the end of it, as we understood that the only thing we need to find is a way to prevent Chrome from overwriting our file. Now, after some times that we invested in thinking about it, we realized that we might already possess this ability. If you remember, one of the results that the fuzzer found was a reproducible timeout, allowing us to repeatedly to bring QuickShell into a state where it repeatedly opens a file that we choose from the downloads folder. So we thought that maybe if right after we send the file, we bring QuickShell into a state where it repeatedly tries to open our file, then since it will be used by QuickShell, Chrome will fail in overriding it. Then we tried this idea, and it was actually the best scenario that we hoped for. Once Chrome finishes the download, the result is that it deletes the temporary CR download file, it fails to overwrite our malicious file, then in its user interface, it reports that the download was done successfully, and clicking on the downloaded file in Chrome's downloads window runs our executable. That was the best thing we could hope for. Thus, we finalized the remote code execution chain that we were aiming for. So we created this demo after the long work that we invested into this RCE chain. In this video, we'll first start by seeing the attack from the attacker's perspective. We'll see that the attacker has set up a Wi-Fi hotspot on its computer. We'll see its IP, and then we'll see how the victim, we'll move on to the victim's perspective, and we'll see how the victim is disconnected from its Wi-Fi network, connected to our malicious Wi-Fi network, and then we'll also see the rest of the exploitation chain. So enjoy. So we're seeing the attacker's Wi-Fi hotspot. We see its IP address. Now we run our tool. We're searching for victims. We find test machine. We choose it as our victim. We see that it's connected to safe breach, but now it's disconnected and connected to test AP. QuickShell crashes. Now we can see all the domains to which the client accesses. Now the client accesses the Spotify website, for instance, to download the latest Spotify installer. We see that the downloads folder is empty, no installer in there. The client starts the download. Let's see what happens. So the download is now finished. We run the executable, and you have bound by SafeBreach Labs. So this is the first example. Now we'll move on to the second. We'll see that the same happens. So we're going inside the Notepad++ website. We're downloading the latest installer. The victim starts the download. The download will now be finished. Victim runs the executable. And again, our malicious malware was ran. Thank you. Okay, so I know it might seem like we found exactly the vulnerabilities that we needed for our attack, but this was not the real thing. Actually, we found two more vulnerabilities. The first one was a limited path traversal to the parent folder of the downloads folder, which is the user folder, but it required to have a very specific name. And the second was another denial of service, but both did not help us to achieve the remote code execution, so I did not elaborate on them. But overall, we found 10 different vulnerabilities, along with another bug in Chrome. Google fixed all the vulnerabilities that were reported to them, and so we set out to look at the fixes. Now, most of them did fix the issues, as far as we could tell, but there were a few surprises. So the first surprise was with one of the denial of service vulnerabilities that the fuzzer found. This vulnerability was caused due to invalid UTF-8 continuation bytes in file names that are being sent to a victim. Now, the example that we provided was a file that starts with a null terminator, which resulted in the exact exception that says invalid UTF-8 continuation bytes. Now, since we provided this example, Google's fix was to just verify that file names do not start with do not contain null terminators, even though we did elaborate on the root cause. So this was surprising, and of course, this was pretty obvious to bypass. All that we needed to do is to replace the null terminator with other invalid UTF-8 continuation bytes, which again resulted QuickShell to crash. So we can again crash it remotely. Another more surprising fix was the fix for the critical vulnerability that allowed us to send files remotely without the need for the user to accept. Now, what we saw is that Google's fix was, instead of just not writing the files that we send to disk in the first place, in the end of a file transfer session, they delete these files. And these files are identified by them as unknown files. So since, and this is the code that does this. So you can see that they're looking for unknown files and then they delete them from disk. So since the files were still written to disk, we thought we had a pretty good chance to bypass this fix. Our idea was that Google probably identifies the unknown files by a certain ID, and each payload transfer packet has a payload ID. So what we try to do is to send 2 payload transfer packets with files as part of a file transfer session. These 2 packets have different file names and different file contents. However, they still have the same payload ID. So we hoped that that QuickShell will accidentally delete only one of the files. And this was actually the case. We managed to send 2 files which were written to disk, and then only one of them was deleted, resulting in a complete bypass of this fix. So we see that we're exploiting the vulnerability again. 2 files are created, and then only one file is left. Okay, so this was Google's response to our original findings. Overall, they really collaborated. We have no complaints. They fixed everything. Also, the bypasses for the fixes that we found. So they were very cooperative. These are the CVEs that they decided to issue. So the 2 first one are for some of the results of our original reports, and the 3rd one is for the vulnerability that I just presented, which is the bypass of the fix allowing to send files without approval. Okay, so by now we probably covered every technical aspect that we can cover, and now it's time to talk about the takeaways, which are just as important. So our first and most significant takeaway is that standard stones may sometimes be forged into deadly drones. And what we mean by that is that as hackers, you often have limited tools at your disposal. You might achieve something, but it's not exactly the thing that you were aiming for. Now, when we thought back on our research, we believe that even seemingly basic or unimpressive abilities can sometimes be transformed into something that is much more powerful. We're all familiar with the typical chains of vulnerabilities that address known issues like bypassing stack cookies or other memory corruptions mitigations, but it's not always that straightforward. Sometimes you might have unconventional abilities, like we had, like forcing an endless loop that repeatedly opens a file. These abilities can be used to create very unconventional flows that still allow you to achieve your ultimate goal. Now, the next takeaway shifts to the defensive side. Many products leave unknown issues and bugs unfixed. due to prioritization. Now, often these issues seem to pose no security risk or only a minor one that doesn't require immediate attention. However, addressing these known issues can sometimes be crucial for mitigating a much larger risk that the vendor might not be aware of. So, for example, in our research, if we didn't have the denial of service vulnerability that allowed us to crash QuickShare, then we wouldn't have been able to establish a forever lasting Wi-Fi connection, which would have completely disabled our entire remote code execution chain. So denial of service vulnerabilities in this case, even though they look pretty basic, they were crucial for our chain. Now, lastly, it is crucial for vendors that develop software to focus not only on specific programming mistakes like memory corruption bugs, and when they evaluate a program's security, it's important to take a broader perspective and consider whether simple logic or intended behaviors might also introduce security risks. So in our case, it's much like the bandwidth upgrade negotiation that allowed us to force a remote victim to connect to our Wi-Fi access point as part of the normal flow in QuickShare. And with this last takeaway, we reached the end. That is pretty much it. This is the QR code for the QuickShell tool that contains all the vulnerabilities, all the exploitation of the vulnerabilities that we saw here today, including the new bypasses that were released just now. You'll also find the contact details of myself and Shmuel, and I'd like to thank everyone for joining this session today. I hope you enjoyed it. I'll be here if you want to ask any questions. Yeah.
Hello, thank you for your talk. And your talk is very interesting. And since you can arbitrarily write any files in the download folder, have you considered the tricks like DLL sideloading, where you just write a DLL file, and then if the victim open an executable file that use the DLL file, then you can also achieve remote code execution?
No, I didn't. We didn't take a look at this attack vector. I'm guessing that what you mean is that if like certain installers might have missing DLLs, right? Then if we'll place the same DLL in the downloads folder, that can lead to that. That's a nice idea, but that will be applicable only for installers that are missing certain DLLs. So we'll have to wait much longer, and then our method will be much more generic, allowing us to, if we define that dictionary with the domain paths, we can define it for various installers. You have other questions? Okay, so thanks everyone. I'll be here anyways if you'll want to ask me more questions.